Hello, 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 hello. Okay. So we are now looking at the some of the we have completed earlier about the surface normal component, but look at these online images. You will be scared. Look at these online images. You will be scared. What it is telling? It is the same thing. This is barrier. This is medium. This is medium two. This is medium one. This is DN1. This is DN2. This is the electric flux. This is X. This is Y. This is permittivity of R1, permittivity R2. This simply represents what DN1 equal DN2 minus DN1 equals to uh, surface charge density. So look at this. Don't get scared. These diagrams looks complicated, but they are just a tiny box across a boundary. What is the problem? Electric field is going from one medium to another. At the boundary, what changes and what does not change? What is tool? Gauss law uses a tiny box, pillbox. This is called pillbox. That is why we see normal TN. That is why we see normal TN. What do we care about? Only the top and bottom faces. Sides become zero when box is very thin. So when box B is very thin, the sides are zero, but the top and bottom will be there. Why do we take delta Z very small? So uh, this is delta Z. Why do we take delta Z very small? Because we are interested in what happens exactly at the boundary. Apply Gauss law. The K enclosed flux to sides equals to zero because area dn at delta x delta y minus delta x delta y equals to delta x. This pillbox area we are calculating uh, equals to rho f delta x divided by this equation will come. So tangentially why it is same on both sides. Take a tiny loop, apply Faraday's law at loop height. The flux term equals to zero, EDL equals to E1t equals to E2t, normal D1n minus D2n equals to 4 plus surface charge density, tangential E1t equals to E2t for tangential electric field, normal BN equals to B1n equals to B2n, tangential H, H1t equals to H2t equals to JS. Sorry, H1t minus H2t equals to JS. These two you can know, these two are understandable. These two tangential by it is same on both sides. Take a tiny loop, apply Faraday's law. Take a tiny loop, means take this loop, apply Faraday's law. What is Faraday's law? As loop height equals to zero, the flux term is zero. Therefore, this net electric field equals to net electric field into the vector quantity equals to zero. Then then E1t minus E2t equals to zero. Then E1t equals to E2t will come eventually. Same happens with V1 and equals to B2. The net magnetic flux around the closed loop for a magnetic field is zero in a barrier. So B1n equals to B2n for the net magnetic field. Simple. If you take another diagram, it is also clear to look. So many teachers explain it in so many ways. Like for this, before this, what is this diagram saying? This diagram is showing how acceleration is split into two different parts when objects moving along a curved path. The easiest way to understand it is to imagine a car moving around a circular road. The blue arrow V bar is the velocity at the point shown on the circle. This is velocity V bar. The blue arrow points along the tangent to the circle. Why? Because velocity always points in an accelerated direction of motion, so V bar is tangent to the path. This is circle is a path. Okay, if you take acceleration, it is taken into two parts. Curved path. The blue arrow V bar at the point shown on the circle. This is the point. The blue arrow points along the tangent to the circle. The blue arrow points along the tangent towards the circle. Why? Because velocity always points in the instantaneous direction of motion, so V bar is the tangent to the path. Acceleration at phase 2 job. The yellow arrow A bar is the total acceleration. So here A bar, yellow arrow is total acceleration. Uh, A bar equals to A tangent plus A normal. So here tangential acceleration equals N equals to normal acceleration. So this is A normal. This is tangential acceleration. It is represented as V. Here An is represented in a circular ground. Like if you take a circular path, circular road. Imagine a car is moving a circular road. Like this is a circular road. The car is moving. When the tangential takes the instantaneous direction of motion, it is v bar. Then An takes the normal acceleration. So total acceleration is the resultant of both. The diagram showing the yellow arrow here is represented. It can be divided into. So this original acceleration is divided into tangential acceleration and normal acceleration. The diagram is saying the acceleration doesn't necessarily point only in downward or only along the motion. It may have both components simultaneously. Tangential acceleration at is the component along the direction of velocity. At equals to dv by dt. It tells us if the object is speeding up or slowing down. If the car speed changes from 10 meter per second, 15 meter per second, this is the tangential acceleration. Its direction is along the tangent. This is velocity, this is tangential acceleration. So AT changes the magnitude of velocity. Tangential acceleration changes the magnitude of the velocity. It tells us is the object speeding up or slowing down. Why this tangential acceleration is calculated? It tells us the object is speeding up or slowing down. For example, if the car speed changes from 10 meters to 50 meters, there is a tangential acceleration. If direction is along the tangent, will also change. So it changes the magnitude of velocity, normal acceleration here. Look at the purple arrow in your image. Points towards the center of circle for circular motion. N equals to a square by r. This is the derivative of magnitude of velocity. This is e square by r. Velocity is x square by r. This component exists even if the speed is constant. Why? Because velocity is a vector. Even if the magnitude stays constant, its direction is continuously changing as the object goes around the circle, and acceleration means changing in velocity A equals to dv by dt. Therefore, changing the direction of velocity produces acceleration. So, AN changes the direction of velocity. The most important idea, tangential, think of acceleration as doing two different jobs, tangential AT, V dt, this forward direction towards center. So, normally is towards center direction. This could be R. Tangential is some this is some error, but this is dv by dt, the magnitude of the derivative of magnitude of velocity. This is what changes, and this changes its direction. Magnitude changes its direction. Here towards center, it is going towards center. So total acceleration arrow is pictured. Resultant acceleration produces combining tangential and normal components. One separate point, if the object is moving in a perfect circle at constant speed, d by dt equals to 0. So it equals to 0. So but n equals to v square by is not equal to 0. Therefore, acceleration points are subject to overflow. This relates to my boundary situation anyway. It is not directly related to the electromagnetic boundary equations we are studying, but your boundary equations come from flame axis. So the diagram is not actually, but why I want to show is we really got concept what is normal component and tangential component. So that's why I will taken different images from the online sources and trying it if there is any relation between. Normal component of electrical density, this is tangential component of electric field is this is normal component of electric field density. This is normal component of tangential component of electric field. This is normal for magnetic flux density. This is tangential component of the magnetic field. Like look at this. These are this topic in itself is a little confusing. Uh, Now I take an anchor diagram. I will see if there is any relation. What this? Okay, my uploads time are over. Okay, uploads time are over. Okay, and we will study next. What is it? What is okay? Completed boundary equation. You come again later if needed. This topic. So what's next for the natural next major section of the boundary equation? Learn electromagnetic waves. That's where we will start connected to or access field and magnetic field population around speed. And this is nice. All the section tells you about what of the new structure generators. So my syllabus, I will look into the syllabus. Um, so planners, I actually found linears. The next topic is boundary radiation. I will be showing plane wave. So ChatGPT is bad when remembering tasks. So careful. Hmm. I think it's plane wave, range, uh, boundary prefecture. Next week, concept of it. Exactly a sequence that according to the framework we have national areas. So next up is concept of radiation. This is an important connection between how electromagnetic waves behave while traveling to how electromagnets are actually produced and radiated into space. The key question will answer is how does an accelerating charge create an electromagnetic wave that can travel away from the charge? This will naturally lead to accelerating charge time varying electron EHCM radiation antenna halfway dipole frequency. Yes, let's continue the concept of radiation from the physical picture first. This is important because if we understand why radiation happens, the half-wave dipole will become much easier. What is an electromagnetic radiation? We already know that an electric charge creates an electric field around it for a stationary charge. The electric field simply exists around the charge. Now, suppose the charge moves with constant velocity, it still produces electromagnetic field, but the important case for radiation is different. When the charge accelerates, accelerating charge electromagnetic radiation. This is fundamental idea. Why does acceleration matter? Imagine a charge sitting here. The electric field extends outward. Now imagine you suddenly move the charge. The field cannot magically rearrange itself everywhere in space at the same instant. The change in the electromagnetic field propagates outward at its unit speed. The disturbance travels approximately at c equals to 3 into 10 power 8 meter per second in free space. The outward traveling disturbance is what we call electromagnetic wave. But by physical acceleration, this distinction is extremely important. Static charge prefers constant position produces magnetic field but does not radiate. Constant velocity charge equals to constant. Produces electromagnetic fields but an isolated charge moving uniformly does not continuously radiate in the ordinary classical picture. Accelerating charge is not equal to zero produces radiation. So remember, acceleration of charge is the source of electromagnetic radiation. Where does an antenna come into this? So now we reach the really important connection. Consider a conductor to an AC source. AC source. The electrons in the conductor are being forced to move back and forth. So the motion is changing with time. Therefore, AC current accelerating charges and increase radiation. That essentially what an antenna does. An antenna converts electrical energy into electromagnetic radiation during transmission. And during reception, the process is reversed. Electromagnetic waves converted to electrical signal. This converts directly to natural equation. This is why your previous topics become useful. Remember the two important Maxwell equations. Change in magnetic field creates electric field, and change in electric field and current is creates magnetic field. Look at the time derivatives, partial derivative of B and partial derivative of D uh, of magnetic flux density and electric flux density. The changing electric field produces a magnetic field. The changing magnetic field produces an electric field. So we get this beautiful idea. We have a change in electric field, magnetic field, electric field, magnetic field. The fields sustain each other as the disturbance propagates to spread the electromagnetic wave. Near the antenna versus far away. Therefore, another important idea is radiation. Suppose we have an antenna, the radiation very close to the antenna, the fields are strongly connected to so this region is called near field. Further way, the electromagnetic wave becomes the dominant propagating field. This is called the far field or radiation field. So conceptually, antenna near field radiation field electromagnetic travels away. We will later study why the field may changes with distance. Why doesn't DC radiate continuously? This is a common exam conceptual question. Suppose we connect a battery to a simple conductor after the circuit reaches steady state I equals to constant. There is no continuous time variation, so there is no continuous radiation like an AC antenna produces. But if we rapidly switch to the current, current we need to then charges are accelerated or deaccelerated during the transition. A changing current can produce electromagnetic radiation due to the time varying currents are fundamental to antennas. The most important picture to remember, don't think the antenna throws electric field into space. Instead, the changing current in the antenna creates changing electromagnetic field, and those changes propagate outward as electromagnetic radiation. So, time varying current, accelerating charges, time varying electric field, or magnetic field radiation. And this is exactly why the next topic in the syllabus is half-wave dipole. The half-wave dipole is basically a cosmology. So, when I studied the radiation, so what I studied is how the radio wave will be created. So a stationary charge has initially it has electric field. So a stationary charge initially will have electric field, but there is a change in charge that thus creates a magnetic field. Uh, Here we will say now suppose the charge moves with velocity, it still produces electromagnetic fields, but the important case for radiation is different. When the charge accelerating, accelerating charge produces electromagnetic radiation. So the idea is simple. When there is charge exists, it simply exists. It is still has electric field around it. So if we take some objects like metals, they also have charges, stationary charges. They have electric field. You know that. So the magnetic field only. will be happens if there are external magnetic field will affect them. Or else we give some battery or voltage, then the electric charge will move. Constant velocity, charges move with constant velocity, it will still produces accelerated charges produces electromagnetic waves, or we call it electromagnetic radiation. Mm, like that is the fundamental idea. Why does acceleration matter? So this is charge. This is the outward means positive. Now imagine we suddenly move the charge. The field cannot magically rearrange itself in the space. A change in electromagnetic field propagates outward at infinite speed. A disturbance traveling approximately light speed. This is electromagnetic wave. This is electromagnetic. The charge is moving. Uh, Due to the disturbance, it creates an electromagnetic wave. Initially, it has a electromagnetic electric field. But by specifically acceleration, this distinction is extremely important. Static charge Q equals to constant position produces an electric field but does not radiate. Constant velocity charge V equals to constant produces electromagnetic field, but an isolated charge moving uniformly does not continuously radiate. The ordinary classical picture, accelerating charge A is not equal to zero produces radiation. So acceleration of charge is the source of electromagnetic radiation. So acceleration shouldn't be zero, then only it produces radiation. Uh, Simply, I said earlier, if you constant position, no movement, then there is still electric field. If there is a movement, velocity, constant velocity, then electromagnetic fields will form. Where does an antenna come into this? Actually, the coaxial cables are connected in like that. There will be inner and outer, right? The outer is connected to the down part and inner is connected to the up part of the antenna. Two parts of the antenna, like capacitor antenna. If you see antenna, it looks like a capacitor if you understand its properties, but it is not. Both functionals are different. The antenna, uh, if you look at this, it looks a complete circuit, closed circuit. Don't think a transmission line is an open circuit with antenna with a load. It is a closed circuit because it has inside conductor, outside conductor. It forms a closed circuit. If here it is inside conductor, outer conductor. At the source, this all forms a closed circuit. Current flows in closed circuit. Where does an antenna come into this? Since they were connected to an AC source, the electrons in the conductor are being forced to move back and forth. So for the AC source, electrons move back and forth, right? So their motion is changing with time. AC current accelerating charges, time varying fields, radiation. That's essentially what an antenna does. An antenna converts electric energy into electric magnetic radiation during transmission and during reception the parts of the electromagnetic wave. So a transmitter, electrical energy is converted to electromagnetic radiation through the antennas. It was the energy is released to antennas. So electrical energy is connected to released as electromagnetic radiation to antennas from transmitter. But here in when receivers, receiver antennas, transmit antennas, there are two kind of antennas. So at receivers, what happens? Electromagnetic wave is received as an electric signal. This connects directly into magnetic field. It is said changing magnetic field is those electric field changing the electric field is magnetic field. Thus, we all studied all this. What here it is, the new thing here changing, telling is we already know what is changing. Electric field changes magnetic field changes electric field. We all know that. But the new thing here we get is near the antenna versus far away. So what exactly he meant by near the antenna and far away antenna? There's another important idea in radiation. Suppose we have an antenna very close to the antenna. The fields are strongly connected to the source. So if this is antenna, the fields are strongly connected to the source. This region is called near field. Other way, the electromagnetic wave becomes the dominant property of it. So we'll talk about this later. I think why doesn't really come. So DC means the current is constant, right? That will not true. So we'll talk later. For this, bye bye.